In 2022, an astonishing image emerged from the depths of space that would forever change our understanding of the Milky Way galaxy. This was not just another photograph of distant stars or swirling nebulae. This was something far more extraordinary. Assembled from the first comprehensive survey using the full array of the MeerKAT radio observatory in South Africa, this image represented 3 years of painstaking data analysis. What it revealed was nothing short of breathtaking and deeply unsettling. Deep within the turbulent chaos at the center of our galaxy, hidden from our eyes for millions of years, were hundreds of highly ordered one-dimensional filament-like structures dangling inexplicably above and below the galactic center. These enigmatic filaments stretch for distances that defy human comprehension. Some extend for up to 150 light-years in length, yet remain impossibly thin, spanning only 1 to 3 light-years across. To put that in perspective, if our entire solar system were the size of a grain of sand, these filaments would stretch the length of a football field while remaining thinner than a human hair. They hang there in the void, silent and mysterious, like cosmic strings plucked from the fabric of space-time itself. The big question that has haunted astronomers for decades remains unanswered. What are these strange, supersized strands? And why do they exist in the most violent and chaotic region of our galaxy? The center of the Milky Way lies approximately 27,000 light-years from Earth. That distance is so vast that light leaving from there right now would not reach your eyes until the year 29,025. Yet, despite this immense gulf of space, modern telescopes have allowed us to peer deep into this cosmic furnace and witness phenomena that challenge our understanding of physics itself. The galactic center is not a peaceful place. It is a realm of violence, chaos, and unimaginable energy. The innermost region, known as the central molecular zone, spans roughly 1,600 light-years and represents, by all scientific accounts, the most extreme environment in our entire galaxy. Consider the conditions that exist there. The density of matter in the central molecular zone is between 10 to 100 times higher than anywhere else in the galaxy. The temperature soars to levels that would vaporize any known substance. The turbulent velocity, which measures the chaotic motion of cosmic fluids and gases, reaches values 1 to 2 orders of magnitude greater than in the galactic disk where our solar system resides. But perhaps most remarkable is the cosmic ray energy density. This measurement serves as a proxy for energetic activity, and in the galactic center, it exceeds typical galactic values by 100 to 1,000 times. This is a place where the universe demonstrates its most extreme behaviors. This region serves as home to vast complexes of molecular gas, containing approximately 20 million solar masses worth of material. Dense cosmic clouds drift through the void, colliding and merging over millions of years. Ionized plasmas crackle with energy, while extreme cosmic ray bombardment fills the space with invisible radiation. Ultraviolet light and X-ray radiation permeate the environment, bathing everything in deadly energy. Turbulent magnetic fields twist and writhe, shaping the very structure of space itself. It is a hotbed of cosmic activity where the universe performs its most spectacular magic tricks. Stars are born here in violent bursts of creation. Supernova explosions tear through the fabric of space, scattering heavy elements across light-years of distance. And at the very heart of it all sits something truly terrifying. Sagittarius A star, the supermassive black hole at the center of the Milky Way. This cosmic monster possesses a mass equivalent to 4 million of our suns compressed into a region smaller than the orbit of Mercury. Its gravitational influence dominates everything within hundreds of light-years. Stars orbit around it at velocities reaching thousands of kilometers per second. Gas and dust spiral inexorably toward its event horizon, heating to billions of degrees before disappearing forever beyond the point of no return. Sagittarius A star is the engine that drives much of the activity in the galactic center, and as we shall discover, it may hold the key to understanding those mysterious filaments. These extreme conditions create both opportunities and challenges for astronomers. The galactic center represents one of the most scientifically interesting regions in our cosmic neighborhood. Understanding what happens there can teach us about black hole physics, stellar evolution, magnetic field dynamics, and the fundamental processes that shape galaxies throughout the universe. But there is a problem. The galactic center is notoriously difficult to observe. Visible light, the type of radiation our eyes and most traditional telescopes detect, cannot penetrate the dense clouds of dust and gas that lie between us and the galactic core. Imagine trying to see a distant lighthouse through a thick fog that stretches for thousands of miles. That is essentially what astronomers face when they point optical telescopes toward the center of the Milky Way. The light simply cannot get through. For centuries, this left the galactic center shrouded in mystery. We knew something significant must be there, but we could not see it. Then came the revolution in radio astronomy. Radio waves possess the longest wavelengths of the electromagnetic spectrum, ranging from a few millimeters to hundreds of kilometers. Unlike visible light, radio waves in the range of millimeters to tens of meters can pass through the obscuring clouds of gas and dust that block our view. They slip through these cosmic barriers like ghosts, passing through walls, carrying with them information about what lies hidden beyond. Radio telescopes opened a new window on the universe, and through that window, astronomers began to glimpse secrets that had remained hidden since the formation of our galaxy. In the early 1982, a young graduate student named Farhad Yousefzadeh was working toward his doctorate using the Very Large Array Telescope in New Mexico. This collection of 27 radio antennas, spread across the high desert, represented one of the most powerful radio observatories in the world. Yousefzadeh was using it to produce a radio map of a section of the galactic center. His research goal was straightforward. He wanted to study star-forming regions, the cosmic nurseries where new stars are born from collapsing clouds of gas and dust. It seemed like a reasonable project for a doctoral dissertation. But as he analyzed his data, something strange began to appear. Narrow strips of radio emission were streaking across his entire survey area, cutting right through the star-forming regions he was trying to study. At first, Yousefzadeh assumed these must be artifacts in the data. Any scientist working with sensitive instruments knows that sometimes the equipment produces errors. Imaging glitches, electronic noise, calibration problems. There are countless ways for spurious signals to contaminate astronomical observations. He tried to remove them through various data processing techniques. When that failed, he attempted to work around them, focusing on the areas of his survey that were not affected. But the strips were everywhere, and they were interfering with his research in the most frustrating way possible. After considerable time spent trying to eliminate what he believed were problematic artifacts, Yousefzadeh made a decision that would change the course of his career and contribute to one of the most profound astronomical discoveries of recent decades. He returned to the Very Large Array to image the same region again, but this time at a different radio frequency. His reasoning was simple. If these strips were electronic artifacts or imaging errors, they would appear differently or not at all when observed at a different wavelength. True astronomical sources, on the other hand, would show consistent patterns across multiple frequencies. The observations were completed, and Yousefzadeh began the tedious work of comparing his two datasets. It was 4 inches the morning when his eureka moment struck. Comparing the two samples taken at different times using different wavelengths, he saw the same structures in both images. This was no artifact. This was a very real finding. Something was out there at the center of our galaxy, something unlike anything he or anyone else had ever observed before. The excitement of that moment must have been overwhelming. Here was a graduate student, expecting to write a conventional dissertation about star formation, suddenly confronting evidence of an entirely new cosmic phenomenon. What exactly was he seeing? Yousefzadeh was observing highly ordered structures in a region where previously only chaos was thought to exist. The center of the Milky Way, with all its violence and turbulence, should be too dynamic for such organized features to form or persist. Yet there they were, displaying characteristics that seemed to defy the chaotic environment around them. The most striking feature was their vast scale. These were continuous narrow strips of radio emission stretching 50 to 100 light-years in length, yet remaining only 1 to 3 light-years wide. They dangled vertically above and below the central molecular zone, oriented perpendicular to the galactic plane like cosmic stalactites and stalagmites. Some of these filaments appeared alone, solitary strands of radio emission hanging in the void, but others appeared in pairs or clusters, running parallel to each other like strings on a harp. Each filament in these clusters maintained a standard separation distance of approximately 1 astronomical unit, the distance between Earth and the Sunday. This regular spacing suggested some underlying physical process was governing their formation and structure. When Yousefzadeh cross-referenced his radio observations with infrared data from the same region, he discovered something else remarkable. The filaments had no counterpart in the infrared spectrum. This seemingly technical detail carried profound implications. Infrared radiation is typically produced by warm objects, by materials that have been heated to significant temperatures. The absence of infrared emission from the filaments told Yousefzadeh they were not producing thermal radiation. They were not glowing because they were hot. Instead, their radio emissions had a different origin entirely. They were non-thermal emissions produced by a completely different physical mechanism. Additional measurements confirm this interpretation. Analysis of the spectral index, which describes how the intensity of radiation changes with frequency, matched the predictions for non-thermal processes. Polarization measurements revealed that the radio waves were organized in specific orientations, not randomly distributed as thermal emissions would be. The data told a clear story. These filaments were highly magnetic, and they were emitting what physicists call synchrotron radiation. This type of radiation occurs when electrons moving near the speed of light interact with strong magnetic fields. The magnetic field curves the path of the electrons, and as they change direction, they emit electromagnetic radiation. The faster the electrons move and the stronger the magnetic field, the more intense the synchrotron emission becomes. This raised an immediate and profound question. What was accelerating electrons to such tremendous velocities? To produce the observed radiation, electrons within the filaments had to be traveling at speeds approaching that of light itself. In everyday human experience, such velocities are inconceivable. Even our fastest spacecraft barely reach a tiny fraction of light speed. Furthermore, the emissions along the length of the structures were continuous. This ruled out localized events like individual stellar explosions or supernova remnants as the source. Whatever was creating these filaments was operating on a galactic scale, producing consistent effects across distances of dozens of light years. Based on these observations, Yousefzadeh dubbed his discovery non-thermal filaments and proposed they were likely related to galactic-scale phenomena. This was a bold claim for a graduate student to make, but the evidence supported no other conclusion. Something extraordinary was happening at the center of our galaxy, and understanding it would require decades of additional research. For a scientist, a discovery like this represented the ultimate professional achievement. Finding something completely new, something that no one had ever seen before, something that challenged existing theories and demanded new explanations. The scientific community took notice, and Yousefzadeh published his findings, establishing himself as a pioneer in galactic center research. But there was a problem. The telescopes available in the 1,980 seconds simply did not have the sensitivity needed to study the filaments in greater detail. Yousefzadeh and his colleagues could see that the filaments existed, but they could not gather enough data to understand their properties, their origins, or their significance. Over the next 35 years, only a handful of other vertical non-thermal filaments were discovered and categorized. Some were given evocative names based on their appearances. The snake, a sinuous filament that curves through the galactic center region. The pelican, named for its distinctive shape. The bent harp, a cluster of parallel filaments with a characteristic curve. These names reflected the creativity of astronomers faced with structures unlike anything else in the known universe. But despite these discoveries, there simply was not enough data to make great leaps forward in understanding. The filaments remained an enigma, a cosmic puzzle waiting for technology to catch up with the questions they raised. If you are enjoying this journey through the mysteries of our galaxy, take a moment to subscribe to Broken Zach. There is so much more to explore together in future videos. Then came 2022 and the revolutionary image from MeerKAT. The MeerKAT radio telescope at the South African Radio Astronomy Observatory represents a quantum leap in radio astronomy capability. It comprises 64 interlinked antennas, each equipped with a 13.5-meter diameter parabolic dish. These antennas are spread over 8 kilometers of radio silent zone, a carefully protected region where radio interference from human technology is minimized. The telescope was constructed over 4 years, with the full array inaugurated in 2018. The location of MeerKAT in the southern hemisphere provides a significant advantage for observing the galactic center. Due to the tilt of the Sun's axis relative to its position in the galaxy, Observers in the southern hemisphere have a more direct line of sight into the central molecular zone and the galactic core. From South Africa, MeerKAT can peer directly into the heart of the Milky Way in ways that northern hemisphere telescopes cannot match. An international team of researchers assembled to exploit this capability. Led by Dr. Ian Haywood and including Yusuf Zada, now a professor at Northwestern University, the team directed MeerKAT toward a 6.5 square degree portion of the sky. To visualize this area, imagine a section of the heavens approximately 30 full moons wide, with Sagittarius A star positioned right in the middle. The team used L-band radio frequencies ranging from 856 to 1,712 MHz, corresponding to wavelengths between 18 and 35 centimeters. This frequency range is ideal for detecting the synchrotron radiation produced by non-thermal filaments while minimizing interference from other cosmic sources. The observational strategy was meticulous. The team divided the target area into a 20-part mosaic, directing the telescope to survey each tile in sequence. The total observation time reached 144 hours on target, an extraordinary investment of telescope resources that demonstrated the scientific importance of the project. This represented the first time MeerKAT's full array was deployed, with 60 to 62 dishes sampling the sky at any given moment. The combined collecting area of these dishes provided unprecedented sensitivity, capable of detecting faint radio sources that previous telescopes had missed entirely. When the observations were complete, the team faced a daunting challenge. They had generated 70 terabytes of raw data. To put that in perspective, this is equivalent to approximately 700 hours of 4K YouTube video content. Processing this mountain of information required sophisticated computational techniques and months of dedicated effort. The galactic center environment is extraordinarily complex, filled with overlapping sources of radio emission that can confuse and obscure the features of interest. To isolate the non-thermal filaments from this cosmic noise, the team employed a technique called difference of Gaussians. This is a commonly used edge-smoothing method that applies a high-pass filter to remove background noise while enhancing the visibility of fine structures. The mathematics behind this technique involves comparing two versions of the same image, each smoothed to a different degree, and subtracting one from the other. The result highlights sharp boundaries and linear features while suppressing the diffuse background. After 3 years of data analysis, the team produced their masterpiece. The resulting image resembles a work of art more than a scientific study. It captures a wealth of features, some familiar and some completely new. At the center, the saturated bright region marks the location of Sagittarius A star, the supermassive black hole around which the entire galaxy rotates. Previously known supernova remnants appear in unprecedented detail, their expanding shells of debris clearly visible against the cosmic background. Star-forming regions glow with the thermal emissions of young stellar systems. One particularly intriguing feature shows a supernova remnant with a runaway pulsar called the Mouse, racing away from the explosion that created it. Another famous feature, the snake, appears on the right side of the image, its sinuous form stretching for over 100 light-years through the galactic center region. But the most startling discovery was the sheer number of filaments apparent in the image. The MeerKAT observations revealed an order of magnitude more filaments than all previously known, with most of them never having been seen before. Where earlier surveys had cataloged only a handful of these mysterious structures, the new image showed hundreds. This was game-changing for Yusuf Zada and his colleagues. After 4 decades of patient research, they finally had enough data to conduct meaningful population studies. "Now we finally see the big picture," Yusuf Zada remarked upon seeing the results. "A panoramic view filled with an abundance of filaments. This is a watershed in furthering our understanding of these structures." The scientific team immediately set to work conducting statistical analysis of the filament population. Their findings, published in the Astrophysical Journal Letters, not only provided further categorization of the filaments, but offered tantalizing clues about their origin. The new data confirmed that all of the filaments are magnetized. In fact, the team discovered that the magnetic field strength in some filaments was significantly greater than expected, reaching 10 to 100 times stronger than typical galactic magnetic fields. Such intense magnetic fields could only be produced by extreme physical processes, further reinforcing the connection between the filaments and the energetic phenomena at the galactic center. The analysis also confirmed that synchrotron radiation is a defining characteristic of all non-thermal filaments, without exception. Every filament in the survey showed the spectral signatures of electrons spiraling through magnetic fields at relativistic velocities. An intriguing pattern emerged from the MeerKAT data regarding how the filaments change with distance from the galactic plane. The observations revealed a steepening of certain spectral characteristics with galactic latitude. In simpler terms, the filaments appear to cool as they stretch away from the galactic center. This seemingly technical observation carries profound implications. The electrons further from the galactic plane could be older, having lost energy as they traveled outward from their source. This age gradient suggested the filaments might be connected to past activity from Sagittarius A star, with newer material near the center and older material extending toward the outer reaches. Another crucial clue pointed in the same direction. The MeerKAT observations revealed enormous structures known as radio bubbles. First discovered by Haywood, Yousefzadeh, and the MeerKAT team in 2019, these massive radio-emitting structures stretch symmetrically above and below the galactic plane. They form an hourglass shape extending thousands of light-years across, dwarfing even the largest non-thermal filaments. These bubbles are thought to have been created by a phenomenal outburst from Sagittarius A star occurring approximately 100,000 to 1 million years ago. To create such enormous structures would require an event of almost inconceivable power. Scientists have proposed several possible causes for this ancient cataclysm. One possibility involves vast quantities of gas and dust falling into the supermassive black hole. As material spirals toward the event horizon, it forms an accretion disk where friction heats the gas to billions of degrees. Under certain conditions, this process can trigger massive outbursts of energy that eject material away from the black hole at tremendous velocities. Another possibility involves a sudden burst of intense star formation near the galactic center. When many massive stars form simultaneously, their combined stellar winds and eventual supernova explosions can drive powerful outflows that reshape the surrounding environment. Either scenario would have triggered an intense release of energy and whipped up galactic winds. These winds would have driven gas and cosmic rays violently away from the galactic center, creating shock waves that propagated outward for thousands of light-years. As these outflows expanded, they would have stretched and amplified magnetic field lines, creating the conditions necessary for both the radio bubbles and the non-thermal filaments. The strong magnetic fields that characterize all filaments provide additional support for this hypothesis. These fields are capable of capturing and confining cosmic rays, the high-energy particles that permeate the galaxy. By analyzing the properties of cosmic rays detected within the filaments, scientists can estimate their age. The cosmic rays observed by MeerKAT match the proposed period of the Sagittarius A star outburst considered responsible for the radio bubbles. In other words, the filaments and the bubbles appear to be the same age, created by the same catastrophic event. The physical association between the filaments and the bubbles provided even more compelling evidence. Using the same high-pass filtering techniques that revealed the non-thermal filaments, the MeerKAT team discovered that almost all of the filaments are confined within the radio bubbles. They do not extend beyond the bubble boundaries, suggesting they were created by the same process that inflated the bubbles themselves. Something powerful enough to create structures thousands of light-years across would certainly possess the energy to accelerate electrons to near the speed of light. The stretched magnetic field lines would channel these electrons along their length, producing the filament's signature synchrotron emission. With this hypothesis in mind, Yousefzadeh and the team described the formation of non-thermal filaments as magnetized streamers in a cosmic ray-driven wind. It is an evocative image that captures the dynamic nature of these structures. They are not static features frozen in space, but rather the visible signatures of powerful cosmic processes that continue to shape our galaxy. This explanation certainly paints a compelling picture for the possible origin of the filaments, but the scientific team was careful to note that it is by no means conclusive. Even as they presented their evidence, the researchers acknowledged that other theories are being developed and tested. Science progresses through the careful accumulation of evidence, and with a mystery this complex, definitive answers may remain elusive for years or decades. What makes these filaments particularly fascinating is their relationship to fundamental questions about how galaxies work. They are not merely a cosmic curiosity, but potentially hold keys to understanding one of the biggest unanswered questions in astrophysics. How do supermassive black holes regulate star formation within their host galaxies? Scientists have long known that the active centers of galaxies must transfer energy and matter into interstellar space through a process called galactic feedback. Without this feedback mechanism, star formation would proceed unchecked, rapidly consuming all available gas and dust. Theoretical models predict that galaxies should exhaust their star-forming material much faster than observations suggest they actually do. Something must be limiting the rate of star formation, returning energy to the interstellar medium in ways that prevent runaway stellar production. Supermassive black holes are prime candidates for driving galactic feedback. When material falls into a black hole, enormous amounts of energy are released. Some of this energy can escape the immediate vicinity of the black hole, propagating outward through the galaxy as radiation, particle winds, and jets of high-energy plasma. These outflows can heat surrounding gas, preventing it from collapsing to form new stars. They can also physically push material outward, removing potential star-forming fuel from the galactic center entirely. But the details of how this feedback operates remain poorly understood. Does energy transfer happen continuously at low levels, or does it occur in discrete, powerful bursts separated by long periods of relative quiet? The MeerKAT observations of non-thermal filaments and radio bubbles provide compelling evidence that outflows from Sagittarius A star happen in discrete but powerful episodes. The bubbles themselves represent the aftermath of one such outburst, an event that released enough energy to reshape the galactic center environment over thousands of light years. The filaments, channeling cosmic rays along magnetic field lines, demonstrate how energy is distributed through the surrounding medium. This pattern of episodic activity has been observed before on even larger scales. The Fermi bubbles, discovered by NASA's Fermi Gamma Ray Telescope in 2010, are vastly larger hourglass-shaped configurations spanning a total of 50,000 light-years. These mind-bogglingly massive structures extend far above and below the galactic plane, visible in gamma-ray observations as diffuse glowing regions. They are thought to be millions of years old, much older than the radio bubbles observed by MeerKAT. The event that created the Fermi bubbles was correspondingly more powerful. Calculations suggest it released energy equivalent to 100,000 supernova explosions occurring simultaneously. This is millions of times more energetic than the current output of Sagittarius A star and comparable to the luminosity of an active galactic nucleus. The existence of both the younger radio bubbles and the older Fermi bubbles suggests that Sagittarius A star experiences periodic episodes of intense activity separated by long, quiet intervals. Each outburst leaves its mark on the galaxy, creating expanding shells of hot gas and magnetic structures that persist for millions of years. Together, these features paint a picture of a dynamic galactic center that alternates between periods of dormancy and explosive awakening. Both types of bubbles have the potential to regulate star formation, ensuring the Milky Way does not suffer from the burnout that unchecked stellar production would cause. The energy they inject into the interstellar medium heats gas and disrupts the gravitational collapse necessary for new stars to form. Over cosmic timescales, this feedback process maintains a balance between star formation and energy injection that keeps our galaxy in a stable state. Understanding these processes in our own galaxy provides a template for understanding similar phenomena in galaxies throughout the universe. The Milky Way serves as a nearby laboratory where we can study galactic physics in unprecedented detail. What we learn here applies to billions of other galaxies, each with its own supermassive black hole and its own history of energetic outbursts. The non-thermal filaments, strange as they appear, may be universal features that appear wherever the right conditions exist. Since the first full-array image was published, MeerKAT has discovered similar filamentary structures in other galaxies. These extragalactic filaments display very similar properties to the ones observed in the Milky Way, suggesting a common underlying mechanism that transcends any single galaxy. Their existence elsewhere supports the hypothesis that they play a fundamental role in galactic processes, emerging naturally whenever supermassive black holes interact energetically with their surrounding environments. If filaments are indeed universal, understanding them becomes even more important. They may represent a previously unrecognized component of galactic structure, as fundamental as spiral arms or stellar halos. Their magnetic properties could influence how cosmic rays propagate through galaxies, affecting everything from chemistry in interstellar clouds to the radiation environment on planets orbiting distant stars. The filaments may even carry implications for questions about life in the universe, as cosmic ray flux is one of the factors that determines whether a planetary surface is habitable. To conclusively piece together the whole picture will require another step change in imaging resolution. Fortunately, that advancement may not be far away. MeerKAT was designed with longer-term goals in mind. The telescope will eventually be incorporated into the square-kilometer array, an international mega-project that will create the most powerful radio telescope ever built. With a total collecting area of 1 square kilometer, the SKA will be 50 times more sensitive than any other radio instrument in existence. It will be able to detect radio sources so faint that current telescopes cannot perceive them at all. The full SKA is expected to be completed by 2028. When it comes online, astronomers will have access to capabilities that currently exist only in imagination. Features within the non-thermal filaments that appear as smooth structures in MeerKAT images may resolve into complex internal patterns. The relationships between filaments, bubbles, and other galactic center features will become clearer, as higher resolution reveals previously hidden connections. Other parts of the electromagnetic spectrum will also contribute to solving this puzzle. Youssef has expressed his belief that the next breakthrough in understanding non-thermal filaments may come from gamma-ray telescopes. Imaging at higher frequencies produces higher resolution observations, with the potential to reveal whether the filaments, the radio bubbles that contain them, and the vast Fermi bubbles are physically connected. Such a discovery would confirm that all these structures share a common origin and represent different manifestations of the same fundamental process. The gamma-ray regime presents its own observational challenges. Unlike radio waves, gamma rays cannot be focused using mirrors or lenses. Gamma-ray telescopes must use alternative detection methods, typically involving the interaction of high-energy photons with detector materials. Current gamma-ray observatories like the Fermi telescope have relatively coarse angular resolution compared to radio instruments. But new technologies are under development that promise significant improvements in the coming decades. Each new generation of instruments opens possibilities that previous astronomers could not have imagined. There is an elegance in the idea of order rising from chaos. The center of our galaxy represents perhaps the most chaotic environment in the Milky Way, filled with violence, turbulence, and extreme physical conditions. Yet within this maelstrom, the non-thermal filaments display remarkable organization. They stretch for dozens or hundreds of light years, maintaining their linear structure despite the forces that should tear them apart. They cluster in groups with regular spacing, suggesting underlying physical laws that govern their formation. They emit radiation through synchrotron processes that require precise conditions to produce. Observing these magnetized streamers flowing outward through cosmic winds reminds us that the universe operates according to physical principles that create beauty even in the most extreme environments. Chaos and order are not opposites, but partners in the cosmic dance that shapes everything we see. The filaments embody this partnership, emerging from violent events yet displaying graceful geometry that spans scales far beyond human experience. Every time astronomers point their telescopes toward the galactic center, they discover something new. The history of this field stretches back more than a century, from early radio astronomy experiments to the sophisticated imaging possible with instruments like MeerKAT. Each generation of scientists has contributed pieces to a puzzle that remains incomplete. Farhad Yousefzadeh, working as a graduate student in the 1980 seconds, made observations that would occupy his entire career. Now a distinguished professor, he continues to study the structures he discovered 4 decades ago. New researchers are joining the field, bringing fresh perspectives and novel techniques to bear on these ancient mysteries. The questions raised by non-thermal filaments connect to the deepest issues in astrophysics. How do galaxies form and evolve over cosmic time? What role do supermassive black holes play in shaping their host galaxies? How is energy distributed through interstellar space? What physical processes create and maintain magnetic structures across astronomical distances? These are not abstract academic concerns, but fundamental questions about the nature of the universe we inhabit. As we continue unraveling these mysteries, the trail shows no signs of going cold. New observations are planned, new telescopes are under construction, and new theoretical models are being developed to explain the wealth of data now available. The MeerKAT image that sparked this latest revolution in understanding represents just the beginning. Future observations will reveal details invisible in current images, answering some questions while inevitably raising others. That is the nature of scientific discovery. Each answer opens doors to new mysteries. Each solved puzzle reveals the existence of deeper puzzles beneath. The non-thermal filaments of the galactic center exemplify this process. Discovered by accident during research aimed at entirely different goals, they have become one of the most intriguing phenomena in modern astronomy. Their full explanation may require insights from physics that has not yet been developed, instruments that have not yet been built, or observations that have not yet been made. But with images and phenomena this spectacular, the motivation to continue exploring has never been stronger. The galactic center beckons, its secrets waiting to be discovered by those with the curiosity and determination to seek them out. The filaments hang there in the cosmic darkness, silent witnesses to events that shook our galaxy millions of years before life appeared on Earth. They carry information about the history of the Milky Way encoded in their magnetic fields and synchrotron radiation. Reading that information requires the combined efforts of observers, theorists, and instrument builders working across decades and continents. The story of non-thermal filaments is far from over. It is, in many ways, just beginning. The next chapter will be written by researchers using tools that currently exist only on drawing boards, studying phenomena that have not yet been detected. Future generations will look back at the MeerKAT observations as a crucial turning point, the moment when humanity first saw the full scope of these mysterious structures and began to understand their significance. If you enjoyed this exploration of one of the Milky Way's greatest mysteries, you will definitely want to check out this video too. It is a great one, filled with even more mind-bending discoveries from the depths of space. And with that, we will see you in the next video.